In this tutorial, we are doing textile inspection. This allows us to familiarize ourselves with the database statistics of the different parameters and with the unsupervised red tool in general. The first step is to add the red Analyze tool. Next, we add the images. Because we need to distinguish good and bad images, we can see that they are named in a specific way. Bad images are here, and they are named with bad in their file name. We have 2 bad images. The other images that just have the number as their file name are the good images. Select all the images and click Open. Now we select an image to select the ROI, which is the region of interest. This ROI can be reduced to see only part of the image, but here the whole thing is fine, and we can click Apply. Now we can select the good and bad images. For this, we need to select images using the display bar. We can type single quote, bad, single quote, and then we get the images that have file names that contain the word bad. Here you can see file name bad001, and here the file name 02. Click Action for 2 views, select Label Views, Bad, and click OK. Next, we select all the good images, so we can add Not to Bad. Or select Not Labeled from the drop-down list. This would correspond with the same 17 images. Select Action for 17 images, and then select Good. And now all images are labeled 19 views, which corresponds with all the images. Now we can tweak the parameters, which are located on the left sidebar. We can see that the mode is unsupervised. The feature size is set to 40. Feature size can be seen with the circle on the bottom left corner. We can verify that the feature size is accurate by selecting the bad images. On the first bad image, we can see that the defect is this long scratch running from the top to the bottom of the image. We need to verify the feature size as it corresponds to this defect. We can zoom in and compare the size of the defect to the size of the feature size. It is good to have a feature size that is slightly larger than the defect. Here, it is increased to 60, and in our case, we see this covers approximately half of the width of the feature size, but the length is much longer than the feature size, and this is acceptable. We can confirm this on the second image. Zooming in on the defect, we see that the defect is covered by the feature size. Again, the feature size is a bit larger, but this is appropriate for our case and in general. The color channel can be set to 1, 2, 3, or 4. In our case, 1 is sufficient. It means that the software will analyze the images as grayscale, so black and white, and this will be fine since there are no specific details on the colors we need to distinguish. The number of epochs corresponds to the number of times that the set of images is seen by the software. So if images are particularly complex and are difficult to analyze, then we might need to increase the number of epochs to, for example, maybe 100, maybe even 150. 200 would be the limit. But in our case, 50 epochs should be sufficient because the defects are relatively obvious. The train selection corresponds to the percentage of images used for training the software. We are using an unsupervised red tool, so the trained images are the good images. Here are 17 images. We are selecting 50% of them, so 8 or 9 images for the training. It is good to have the training at 50% because it allows half of the images to be used as test images. It is important to have as many test images as possible. However, it should not be less than 50% because the software needs as many images as possible for training. And in our case, it could be problematic since we only have 17 views for training, which is not many. In many cases, we may need to increase the training selection to 70%, for example, in order to get better results. However, in our case, we know that 50% is enough, so we can leave it as it is. Capacity can be increased to huge or decreased to small or tiny. We will leave this at large. It is acceptable. It could be increased to huge if the images were very complex. Training passes can also be increased in the case of complex defects. There are also perturbation parameters that can be added. We will take a look at that later. We can now train. The training took approximately 4 minutes on our computer, and we see that all of the images were processed. Results are shown in the database overview on the right sidebar. We can see the results are not perfect. We can see that some of the images are in between the two thresholds, so they are difficult for the software to classify. It is in the intersection here of the matrix. We can click on the numbers to see which image that this corresponds to. We can also move the threshold bars by simply lowering the lower threshold. This allows us to better see what features the software reacts to. If we look at the good images, at the actual good images that are predicted in the intersection by the software, we can see that the software reacts on the edges of the good images. The reason is that the pieces of textile have been cut a bit differently so that the edges are slightly different for each piece. The software considers this a defect. The way to solve this problem is to edit mask and add the border. The border has a width fixed at 40, but it can be changed to match the feature size of 60. This way, the software will look at the whole images up to the new border that was added and stop at the border. It will not reach the edges of the images. This is what is problematic, because when it reaches the edges, the software recognizes that there are parts outside of the image. The software will identify defects that are not really a defect because of the variety of possible configurations near the edges of the images. Now that we have implemented the mask, we can click Apply and click Yes. We want this applied to all tools in all views. And we can process. Now the separation between classifications of good and bad images is much better. We can now fix the thresholds so that there are no images in the intersection between good and bad predictions. We now have a more robust classification. Now let's take a look at some of the other parameters we can adjust, the perturbations. There are different types of perturbations: rotation, scale, aspect ratio, shear. They are the geometric perturbations. We can also flip the image horizontally, vertically, or both. Then there are luminance and contrast perturbations. What the perturbations do is generalize the defects that we have. If we look at the bad images, and we only have 2, so these are very specific defects. The best data set that we could have would contain many different examples of defects. In a case where we do not have such a data set, it is interesting when we add the perturbations, because this artificially creates more defects. Adding perturbations modifies the defect slightly, and thus we obtain different defects. One example of this is in the bad image. It generalizes the training and makes it more robust. In the case where we would like to apply this to a large number of images, an example of the parameters that we could adjust would be, for example, changing the aspect ratio to 5%, so we can see here on the animation that the letter F is increasing and decreasing in size. And what is interesting with this perturbation is that the increase or decrease is randomly on the horizontal or vertical axis, so it brings interesting deformations. We also add the 5% shear. And we again observe the letter F is tipping forward or backward slightly. And this would make this scratch tip slightly to one side or the other. Therefore, we expect the software to react less strongly on the particular defects that we have. However, it would be more robust for the general model and would be better for the application with many images. Let's have a look by training. After training, we observed that the results are actually not that different than before, and we would have expected in the results that the defects would have been harder to find for the software since we added perturbations. So, for example, bad images could have a score that would be lower and closer to the good images. However, the perturbations that we added are still low, only 5%. That may be one reason. It is generally good to add perturbations, as we saw, to make the software more robust.